Is I audible? Good morning, all of you. Today we have three lecture sessions by Professor Ravindra Pandey sir, followed by a tutorial session by the local host faculty. Today's lecture is based upon the characterization method, introduction of batteries, photovoltaic cell, and hydrogen storage devices. I welcome Pandey sir to present their talk. Thank you. No problem, sir. You may continue.
Namaskar. So let's start the day. So it's the day 2. First lecture is going to be. So I changed the little bit sort of the topics. Dr. Bhavna Singh announced. I'll talk about the battery, but I thought let me do the imaging and a little bit about quantum mechanics and solid physics. So I have like one day a little easier, and then today is little more mathematical equations. Tomorrow is going to be a little easier, and day 4 will pick up more mathematics. So we start with the summary is what we learned yesterday, that we had to define the structure property relationship of a given material. Then only we can use them for energy applications. And we discussed about a little bit about what kind of tools we have available from simulation and theory to design these materials. Then we looked into nanomaterials, how good they are, and then what is the specific properties. And we came to know that indeed nanomaterials provide a very, very large surface area to provide the significant reactivity or activity for a given material. But at the same time, they have the so-called quantum confinement effects, which we can exploit for novel devices or novel materials. And then we looked into some of the synthesis methods, how to make these materials. And one of the methods is CVD, is going to be very, very useful in scaling up the process from lab to pilot plant to industrial scale. And then we looked into this 101 solid-state physics, is that we have really help from mathematicians to basically do the Fourier transformation and go from a real space, a direct crystalline lattice to reciprocal lattice, which gives us sort of access to the diffraction data in X-ray diffraction to understand the periodicity or the structural information about the material. And then also we looked into it because the crystalline material, they have the periodicity, and this periodic potential then leads to so-called the band structures in a given material. So before I go to day 2, do you have any questions about the homework? Any chat messages or any questions? Did they manage to submit the homework assignments? How much time did it take? Few minutes or few hours? No feedback? Okay. So let's look into the characterization, and we will focus on the so-called the electron-based the methods coming into the play, and especially we look into now is the imaging techniques. Yesterday you had X-ray diffraction, and today we will talk about imaging techniques. And the advantage what we have is we can definitely understand what are the signatures on the surface. From there, we can understand the fundamentals of physics and chemistry of the material. And then we look into one of the powerful tool we have is a Raman spectroscopy, which provides so-called these vibrational signatures of a given material. So what it does, it tells us what the kind of the bond and what is the strength of bond of a given material, especially like if you go from the 0D material of fullerene C60 clusters to 2D graphene or a 1D carbon nanotube, and then we have 3D graphite. So it sort of tells us the progression of the strength of the bond going from 0-dimensional to 3-dimensional. So this is a sort of a sketch which tells you the length scale on the x-axis, and then we have time scale. And if you start from top, you can see the optical microscopy really provides a larger length scale and about a few seconds. But the information is still is a kind of a vague, we do not have the details. So we have to go down and we come to the scanning electron microscope or transmission electron microscope, and you begin to see the structure information in about a nanometer length regime. And then from once you go to so-called high resolution TEM, you can really map out the atom by atom in any given material. So this slide I showed you yesterday, just give me a second, I'll do my that we have the magnification in 3D using the atomic force microscopy, which sort of tells us the how good the strength of the bond or the mechanical response is. It does also provide the high contrast. And then we have a scanning electron microscope, which sort of deals with the 2D magnification with a very high depth of field, but also tells us what kind of atoms are on the surface, giving their chemical information about the chemical composition. So, especially using AFM, you can see here is we can definitely see the nano-sized, nice rounded gold clusters on a copper substrate. So this is again is a sort of 101 about these electron-based spectroscopic methods. So what we are looking at is the signals coming out, the interaction of the electrons when they bombard on the surface. So initially when it starts from an electron gun, which has a tungsten filament cathode, and we have a thermo-ionic emissions from this gun. And this beam is very, very well focused, and especially of also low energy, is about 40 kilovolt as an electron probe. And if you go further beyond 40 kV, then you may damage the sample which you are studying and investigating it. So this is a cartoon, is about what exactly is happening. So once the electron beam hits the sample, and a lot of processes occur, and we have the scattered or emitted electrons coming out. You can see here from deep down, we have the X-ray coming on, and then we have also the luminescence coming from the cathode luminescence. But if you look at the scattered part, we have the back scattered electrons coming from the back of the sample. Then we have OJ, and then we have secondary electrons. So what we have is here is a detector detecting all these sort of scattered or emitted electrons or photons. And from there, it gets the information and sort of scans across the surface. So this is, again, is a coming out of this SPM, scanning probe microscope, where you can see the xenon atoms atom by atom, you can place out and deposit it on a nickel, and you can sort of look into their the morphology and size using SPM. So what it does, it definitely allows us to image at a nano or a really atom scale. It also allows so-called atom by atom manipulation, and it can be used especially in the tunneling current characteristics about to characterize any given device made of these 2D materials. So what it does is scan a sample surface while measuring in a sense of two types. First, we look at the force versus displacement, and that's called the atomic force microscope. And if you look at the tunneling current characteristics, and it turns out we refer it as a STM, scanning tunneling microscope. So STM is really gets down to into details, and you can see here a 10th of nanometer resolution, which we can image the objects. And since it uses the sort of it's a probe, which is nothing but a small tip, sort of forms a tip, and then this piezoelectric scanner, the form of the material of the tip, scans across the surface. And its sensitivity, because again, we are looking into the tunneling current, is very, very high because this depends on the exponential dependence of the current on the distance, how far you are from the surface. On the other hand, if you look at the atomic force microscopy, AFM, what it does, it sort of senses the repulsive and attractive forces from the surface. And so because of the force, the distance dependence is a part of the measurement, then it depends on so many other factors also, including tip shape or surface area and so on. So this is again is a cartoon which tells you is what's the sort of STM look like. So we have a sharp conducting tip, especially it could be the platinum or a nickel, depends on what kind of measurements you would like to do, either spin allowed or spin not allowed. And once sort of it scans the surface, and then it's connected to this sort of applied bias. So what you are doing, you're measuring the tunneling current as you move across the surface. So it depends, scan this way, but it depends on the distance between tip and the surface. Then we have because of this tunneling current characteristics, we can definitely go down to the position control about a 10th of a nanometer. And this is, again, is a very, very small device. You can see in the left corner. AFM is also, as I said, sort of measures the force of attraction, repulsion between the probe, the tip, and the surface. But what we have here is this tip is attached to a cantilever. And so which sort of moves up and down is very, very sensitive cantilever. And we can also amplify it by laser or a photodetector in this case. This is here is a sort of, again, a cartoon, very small device, which can be used for AFM measurements. This is the graph is coming out from the graphene on silicon carbide at about 1.5 volt bias. And what you can see here is a DI over dV. So we are looking at the conductivity thing. And as depends on the voltage, applied voltage. And you can see the difference between a black is a monolayer graphene and the bilayer is in red. And the conductivity definitely increases as you go from mono to bi. But again, you can see the sensitivity changes, which you can see on the graph. On the right is a bilayer related to the monolayer, which is really clearly all these hexagon rings are visible within this nanometer length scale. On the other hand, is the AFM definitely can be used to look into the monolayer or bilayer or trilayer, the multilayer thickness. And here I really want to point out, look at the sensitivity here. is we are talking about the 1,000ths of a nanometer, where you really can see the step height on the red part is about 0.274 nanometer. And if you look at the other is you have the tri-layer case, you really can measure the step size about 0.620 nanometers. So they are really powerful tools, but again, it's very, very expensive also in terms of the. So any questions, comments about SPM, STM before I move on to Raman? No? Okay, so let's move to Raman. So as we know, is a great scientist. We had Dr. C.V. Raman. And if you had a chance to go to Jabalpur, IACS, still they have maintained the basement, the instrument which Dr. Raman has used to discover this Raman effect. So what it does, it exploits the properties of phonons. And like a photon, a light, we have the quanta that have the energy of lattice vibrations. Because as we know, is as we increase the temperature, these atoms, because of the thermal energy, they tend to vibrate. So through Raman spectroscopy, we are really probing these vibrational modes of a given material, which depends on the strength of the bond. That's the key thing here. So that's a little on right. I just want to refresh. We call this elastic scattering. Whenever we have the scattered light, lambda scattered is equal to lambda incident. But then we have inelastic scattering when they are different from incident lambda to scattered lambda. So what does the Raman do is it probes the inelastic scattering of light by these phonons. So photon comes in and gets scattered. And the scattering light has information about the phonons. There's a nice equation describing the contribution of phonons and how can extract the information. And now we're talking about the crystal structure, and I've not gone into detail about the group theory. This is again is a very powerful mathematical sort of a tool we have where we can look into the symmetry classes. So what we have is the so-called Raman active modes, because not all the vibrational modes are active. You can see their signals. So for this group theoretical treatment tells us that all the modes which belong to a certain symmetry class are going to be Raman active. And so this is mainly vibrational, but now also we can extend the analysis to sort of look into the rotational modes also in a given samples Raman spectrum. So the key thing is here is like I've been sort of emphasizing is we can probe sort of the strength of the bond, in this case of a molecule, because again, using a quantum mechanics, which I'll show you a little later, that each bond, say, if you look at the graphene or say H2O or H2, the hydrogen. So hydrogen bond, it corresponds to, we can sort of simulate that bond in terms of a potential well. And then you sort of, you have the wave function and you have the potential, and you can then do the mathematics to find out so-called the eigenstates. And these eigenstates are going to be called occupied states, which are definitely going to be bound state because H2 is stable. And then you have so-called the unoccupied states. So the key thing is like I said, is the mode which is going to be Raman active. It sort of has the requirement that a molecule must undergo a change in pulsability during the vibrations. And as we know, pulsability you can understand in terms of the flexibility of electronic cloud of that molecule. If the molecule has a really flexible electronic cloud, then you have the high polarizability. And if you don't have, then it's going to be low polarizability. And you can see the difference between, say, fluorine and a rare earth or the noble gases, noble metals, xenon or gold, other stuff. They are low polarizable atoms, and fluorine, chlorine, even carbon is a sort of a highly polarized. If you look at the without any external field, without any perturbation, we have a nice sort of electronic density in blue, which is unpolarized. But once you apply the external sort of perturbation in terms of the electric field, or even in terms of the optical or laser field, photons, you can see there is a disturbance, and this molecule gets polarized. And then only can sort of gives the so-called these Raman active mode. So polarization of a given system is very important to use the Raman to characterize the materials. So this is a typical standard example in the textbook. We pick up a nitrogen molecule. And as we know, the bond is pretty strong. So it's about what they call triple bond. Chemists can understand. And if you look at the Raman shift, so what is the Raman shift is we go to this left cartoon, we shine a light with a given wavelength of a photon. So because of the molecular, we can simulate in terms of the called harmonic oscillator model, which provides these vibrational states in terms of the energy levels. So you have a given vibrational states down here. The excited photon, it goes to so-called the virtual states, around excited states. And it comes back to the same ground state, then we refer to the scattering as a Rayleigh scattering. But for the Raman cases, we have a called Stokes shift or anti-Stokes shift. And here in Stokes, you can see we shine the light, so electron goes up here in the virtual or excited state, and then after a while it comes down, but it does not come down to the ground state, but some of the other higher vibrational states. So then the excited or the emitted, the energy is smaller than the incident we call the Stokes. In the other case, the here excitation is from not the ground state, but one of the higher states. So it goes there, and when it comes back to the ground state, so we call the anti-Stokes shift. So these are the nomenclature to look at the Raman shift. This is called Raman shift. And it goes again from very, very low wave numbers. If you look at the rotational part, about 100, 150 centimeter inverse, to very high, about 2350 wave numbers, inverse wave numbers, because this nitrogen-nitrogen bond is very, very strong. So let's look at our carbon-based materials. What happens in fluorine, and we'll tell a little later about the bonding. Is what we call is these are the sp2 kind of bonded spherical carbon cages. It has a IH symmetry, and applying the group theory, we can sort of find out mathematically that this carbon cage, fluorine C60, has a possible 46 vibrational modes. And if you look at the Raman shift here, you can see is the so-called the AG1, we call it, or AG2 mode. So AG2 mode is at the 1447 centimeter inverse, and AG1 is about 500 centimeter inverse. And I can tell you it comes from both either pentagon or hexagon of this sp2 bonded cage. So just to give you an idea, is earlier we saw nitrogen-nitrogen bond sort of gives about 20 centimeter inverse Raman shift. But if you look at the C60, it comes down to about 1450. So from here, you can see, it's nitrogen relative to nitrogen nitrogen bond, carbon-carbon bond is little weaker. Although it's strong, it still is weaker than NN bond. Now let's look at the carbon nanotube. Then we have so-called, and again, is deployed on sapphire substrate. So in sort of yellow, you can see the substrate signal is coming out pretty high, about 1400 centimeter inverse. But depending on the incoming photon, here we are going from 488 nanometer from blue to 633 nanometer, which is kind of a red. And depending on the case here, you can see the shift and the shape of these Raman peaks. So it depends on what kind of wavelength do we use to characterize the material. And this band is about 1592 centimeter inverse or 1600 is referred to as a G band. So the materials community, people always ask, what is the G band for a given sample? If it comes out around 1592, then say, aha, you have a very, very nice crystalline single wall CNT. So you can use the position or location of G band to characterize how good your sample is. And then if you do the mathematics, you can find this band is nothing but is an in-plane bond stretching mode of the CC band bonds in the hexagonal lattice. Let's move to graphene now. Now graphene gives a little different signal, and it has both so-called G and G prime bands. So G band is you can see here, is coming out, it's split. I can tell you a little later about the splitting, but we also have G prime, what we call is a little higher frequency. And what we say is basically is a breathing mode. So in the hexagonal lattice, these hexagons sitting there, they breathe. And you can see is in terms of a stretching mode of a single CC bond, the breathing mode is going to require a higher energy. And this is why is at the higher shift is a higher wavelength inverse related to G band. So this again slide summarizes is as we go from graphene to single-walled nanotube, carbon nanotube. And I have another sort of thing is called HOPG, which is another form of sort of a graphite. But you can see here is in the single-walled nanotube, carbon nanotube, we have the G prime band is very, very small. And the graphene G is again at the same location, but is little broadened, is a little broad peak. So what is happening here is basically, if you look at the graphene sheet and the single-walled nanotube, basically what you are doing is you're introducing the strain effects, what you call, because of the curvature. So what it does is if you see the G prime band, which is the breathing mode of these 6 carbons, and once you introduce this curvature effect or strain effect, it goes away. So in a sense, the breathing mode is in a sense is not allowed or is very difficult to show up in a carbon nanotube related to graphene. And the G band, you can see, is simply a stretching mode of carbon-carbon on a plane. So it does not matter is a planar structure or is a curved structure. And you can see from here is a very nice tool to understand is how large the strain effect is, which we can see the splitting of the peaks in the G band. So you have a very, very small diameter carbon nanotube. You can see the strain is going to be pretty large. So you're going to have a larger shift. But if we have a very large diameter carbon nanotube, the shift is going to be small. So from using this input about how big or how small the shift is, you can sort of characterize your nanotube being a smaller diameter or a large diameter. So let me summarize what we have seen using a force versus displacement, because of the cantilever can sense the forces and depending on attractive and repulsive as it moves along the tip on the surface in AFM. And the tunneling current characteristics can be used in STM, but also it can be helpful in understanding the device characteristics based on these nanomaterials. And Raman basically relies on this principles of inelastic scattering of light by phonons, because this inelastic part contains the information about the phonons. And then we saw that G band is really important, sort of a signature of on these carbon-based materials, which tells about the CC bond stretching mode. Okay, so any questions, comments? So how much time do we have now? I'll move to the other part. Is half an hour, I think we've done it. So now look into the bonding. We talked about sp2 bonding, but let me go into, I call chemistry 101, is to refresh your memory about what exactly the bond is, which again we can see is going to be important to understand the results coming out of theoretical simulations using these methods. So let's go to the basics. I call the 9th grade chemistry. And we have is atomic cohesion. And I pick up the example of a hydrogen molecule. And you can see is the atom, and then it forms the molecule. Then the overlap occurs, the electron density. So on the right, you can see here is this overlap. If I look at the nuclei, definitely the bond center, instead of having a single atom, there's some charge density or the overlap sort of kicks in between the molecule, between the atoms in a given molecule. And what we say is this sort of provides the stability or the cohesion. And on the right, if you can see, if I pick up your screen sharing is paused. Why? Okay? Oh, I see. It's not on the full mode. Give it just 2 minutes to make it the full mode. So I talk about this cohesion is this typical 9th grade chemistry, if you remember, is we come in from hydrogen atom to hydrogen molecule, and what you have this overlap of the electron density during the bond center audit. So we can treat the nuclei as a classical point charges, but in quantum mechanics we now move to the wave function. And what the measurable quantity, what we have is we can express in terms of the probability density, which is nothing but the square of a wave function, and we define it as a rho r. So you can see here is when we had the hydrogen atomic orbitals, which is a 1s electron and a 1s electron for the other atom. And once they form a bond, you can see the energy sort of comes down, and these electrons are now is they spin a line up and down, giving a so-called the sigma bond, sigma level, 1s. And then this is the virtual level as a sigma star 1s or for the given molecule. So when you excite the photon, basically what you're doing, you're exciting this electron from sigma 1s to sigma star 1s. So what we can do is for the given wave function, now we bring in so-called these quantum numbers, and I'll tell you later about the Bose model where the quantum numbers come in. And we have is three kinds of quantum numbers. It's N, L, M. So wave functions, when you see psi, is definitely going to have N, L, M as a subscript, defining this wave function represents which state, which of the polarity, and what kind of the spin. So N principal quantum number can have values from 1, 2, 3, so on. And depending on the N value, then we have the L value, which we define in terms of the S, P, D, F, G like wave functions. If L is 0, is going to be S. If L is equal to 1, is going to be P. If L is equal to 2, is going to be D. And the spin up and down then becomes the +1, ±1, and plus half, minus half. And then available number of ML values go from minus L to +1 to +2 and so on. So for a given, say if I pick up a sodium and fluorine, which has a electronic number 11 and 9, and once they form a bond, we can see the charge gets transferred from sodium to fluorine, and we have a nice sort of ionic bonding. What we call is Coulomb interaction energy, which is sodium fluoride is much more stable compared to isolated sodium or fluorine atoms. So in a sense, what I call is the hand waving argument is the stability of a given molecule is going to be governed by this overlap of wave function, which is again indeed has the origin in quantum mechanics. So the overlap of charge density gives us the stability. And depending on the case, in this case is the Coulomb interaction energy, but we can have the other cases of bonding, which I'll go through it. So sodium fluoride sort of provides us the example of ionic bond, but in carbon-based materials, what we have is sort of the covalent bonds. So if you look at the plotting the distance and the wave function, so if I look at the nuclei, and when they form a bond, you can see there is definitely the overlap at the bond center. 0 sort of provides the bond center. So if I bring in the wave function, and this is a p-type wave function, and if you remember, p has 3 components because p is L is equal to 1. So we have a px, py, pz, or pz. So for these p-type orbitals, when they come in and they become so-called the directional bond, you can see the bond definitely is going to be in this axial direction for this case. And this is a simple sort of a representation of bonding graphene between pair of carbon atoms. So if you look at all if you pick up the carbon, and as we know, carbon has 1s2, 2s2, and 2p2. Okay. So our call is that we have the core 2 electrons belong to 1s, but we have this 2s2, 2p2, so-called the 4 valence electron. So if I look at the s-type orbital, let's say spherical shape, again coming from the quantum mechanics, because L is equal to 0, is symmetric. But Px, Py, Pz is going to have symmetry along the axis. So Px is going to be along x, y, and z. And here you can see the so-called the blue and the gray represents we call is a plus or a minus component of a wave function, psi plus or psi minus. Now we bring in these two carbon atoms. So what they're going to hybridize, we call this overlap of a charge density of wave function as a hybridization. So if we have the 1s, 1p, we call sp orbital. You can see it's real line. If we have 1s, but 2p orbitals, it's called sp2 orbital, and they form this kind of a shape with a certain degree of angles between them along with reference to the axis. And when we have a 1s, but 3p orbitals, we call sp3 orbitals. And it is as sort of a tetragonal shape along x, y, and z direction. So this sort of, again, gives you what we can do using our simulation methods or theory. You can really look into the charge density of at the interface of these given materials. So I picked up the case here. We have a metallic clusters, manganese, silver, and aluminum. And they're interacting with a molecule called dopamine. Dopamine has a sort of a carbon hexagon ring with some nitrogen and oxygens at the periphery. So if I pick up this molecule, you can see molecule has this carbon ring, means the PZ or PZ electrons are perpendicular to the surface. So they form this called the pi electronic cloud. Now I bring in the cluster. Now manganese has the d electrons. So you can see here is the d really loves the p electrons. And from again in chemistry 101, we know PD hybridization is pretty favorable. They like each other. But if I go back to aluminum, aluminum is a p-type material. So these are pi electrons, which are a pz electrons, and they see another sort of p electron cloud. They don't like each other. So they are still repelled, So they are not significant. There's hardly any overlap between these two, cluster and molecule. But if we look into the silver, which is a S-type, and then we have the P-type, the dopamine molecule, you say there is some overlap, but this SP hybridization is not as strong as a PD hybridization. So by looking at these, doing these calculations, you can definitely see if manganese, is it going to interact with a certain molecule related to either silver or aluminum nanoparticles. And from there, you can induce or deduce the information about how toxic or how deformed the interaction is going to be of the conjugated system related to the pristine systems. So if I look at back to carbon-based materials, so we talked about, again, is a 1s, 1p, is the sp type bond. I can see is definitely they are going to prefer in sort of aligned way, is a linear way. So we call it the polyene chains. You can see it's definitely they are sp sort of base compound, bonded compounds. But if I go to now S, 1s and 2p's, in this our case 2s and 2px and 2pz orbitals, py, you can see it prefers sort of a planar arrangements. But if I go 1s and 3p's, and then you can see here is what we have is it's sort of going to lead us to the three-dimensional interconnectivity. So you can easily infer from here is we have the polyene chains going to have sp bonded system. For planar like graphene, it's going to be sp2. And then we have 3D, like a graphite, is going to have a sp3 bonded system. So what happens in this of the force and the potential energy when we bring in these atoms and form a compound? So we are moving from the molecules to solids. So if I go to very, very large distance between these two atoms, if I look at the force between them, is going to be almost nothing. It's very, very little. Now I bring in these two atoms in a given crystal slowly nearer to each other. And you can see here is if we have the say positive and negative is going to attractive. So the attractive force sort of arises, you can see. But at certain point, what happens is these nuclei now are very near to each other. So the electronic attraction now is being taken over by the nuclei repulsive forces. And you can see it goes down to significantly. And this is what we call is the internuclear distance R naught. Same thing what happens if I go from force to potential. And as you know, potential energy is a derivative of force. So what you can see here, the large distance is the potential energy is very small. We bring in, so this is attractive energy, but at R naught, when it comes down close to, it rises because it becomes a repulsive here, this energy. So what we have is, this is the formation of the equilibrium configuration. So at that point where our energy is minimum, and this is called the binding energy of a given system. Is what we gain from the energy at a large distance to energy at the equilibrium distance. This is our equilibrium distance, and this is the binding energy of a given system. So this is again is the cartoon which I just talked about. And then this is a small sort of integration coming from the energy from the force, and it could be the attractive or the repulsive. And from here, you can sort of get the information about what is the attractive energy, potential energy, and what is the repulsive part for a given system. So these bindings, what we call the primary bonding, as you know, is ionic. When we have transfer of valence electrons, then we have covalent, like a carbon-carbon based systems, is always going to be a directional. That's a key factor, and sharing of valence electrons. Or we have a metallic electron, which I have not gone through it, is basically we have the delocalization of these electrons. So we call it like a free electron gas. Electron can move easily in a metallic system, which we know. But we do have is so-called the weaker part, which is we refer to a van der Waals bonding or secondary bonding, and which arises in either hydrogen-hydrogen bond or so-called dipole interaction. And then again, it can have polar molecule or fluctuating dipole interaction. But they are very, very weaker compared to these bonds. So what happens in the material, depending on the strength of the bond? So we can definitely use the information to both the equilibrium bond length and the bond energy to look at the melting temperature. And what you find is the melting temperature is larger if our bond energy is pretty large. So there's a one-to-one direct relationship between how strong the bond is and how high the melting temperature is. And you can see here in this table they are really directly related to each other. It doesn't matter what kind of bond you have. So if the first two cases, ionic bond, you can see the MgO, the bond energy is pretty high compared to NaCl. And it does reflect in their melting temperatures. MgO melts around 2800 degrees Celsius, while the sodium chloride is about 800 degrees Celsius. If I look at the covalent bond, we have example of either silicon or carbon, which is a diamond. And you can see here, diamond is the stronger bonded compared to silicon, and it does reflect in the melting temperature. Here is about 3,500 degrees Celsius, and silicon melts around 1,400 degrees Celsius. For the metallic bond, and if you go from mercury to aluminum to iron to tungsten, and you can see here the increase in the bond energy as you go to mercury to tungsten. As we know, mercury is in liquid state at room temperature, but if you come down to aluminum to tungsten, the bond energy is almost 3 times. You can see here is also the melting temperature has gone up tremendously. So knowing the bond energy, you can sort of predict how stable the compound is going to be. We also can get some information about the mechanical property. So what we have is we can define the elastic moduli, elastic modulus, in terms of the force. And force is nothing but the derivative of the energy. So if you look at here we have the new underform, the equilibrium configuration or the deformed configuration, we can calculate the energy. So the energy is, elastic modulus is large because we're talking about the force, which is derivative of energy, means we are looking at the curvature near the equilibrium separation. So if it is large curvature at the equilibrium separation, Young modulus is going to be large. If it's small curvature, you can see there's going to be small. So definitely using the knowledge or the information about the structure of the bond, you can either look into the stability of the compound or also how going to be strong really in terms of the mechanical properties, the elastic moduli. That's very, very useful information if you want to apply to energy or electronic applications. So summary is we talked about mainly ionic and covalent bond. Ionic we know is non-directional because there is an electron charge transfer and tend to be sort of occur or is there in ceramics, the oxide materials. And the covalent bond is a variable. It goes from very, very large for diamond and very, very, very small for bismuth-based compounds. And you can have, again, it's going to have directional bonding, which again occurs in semiconductors. Some of the ceramics are polymer chains. And metallic, again, is a non-directional. And it does vary. It's very large for tungsten. That's why it has a high melting point and very small for mercury. And the so-called the van der Waals bonding is going to be very small and depends on which kind of material you're looking into it. So let's look at the cases. What we have thing is the 3 slides. 0D, 1D, 2D for our carbon-based materials. So as we know, this is sort of a cage material. But what it has is so-called the pentagons, the 5 carbon rings, or we have hexagons. So depending on the case, penta and hexagon, you can see here we have a carbon single bond or double bond. And single bond is going to be little at a higher distance. And the CC bond is going to be 1.45 angstrom compared to the double bond, which is about 1.38 angstrom. And again, is because of this thing is the C60 are a very good so-called electron acceptors. They allow to grab the electrons and definitely can increase the efficiency of solar cells. So Vijay, Dr. Hinge is the question is very correct, but see is W and tungsten and the silicon. The case is we are talking about the covalent bond and metallic bond. So there is a direct relationship between the same nature or same bond, compound, which is similar bonding. So we can compare covalent within the covalent bond system, silicon with carbon. But tungsten comes in the metallic bond category. So we can compare W with other metallic compounds. Does this make sense? Yeah, within the bond group. Yeah, you're right. So we have the ionic group, the covalent group, and the metallic group. Yeah, good. So the 0D is you can see here is sp2 bonded, but we have the different sort of a single or double bond, the strength. And if you look at the graphene, is a very interesting material in a sense. We have these the 1s and 2p type sp2 bonding. So what is happening here? The directional bond along the bond. This gives a very strong, but we have so-called the the electron sitting is perpendicular to the surface. So the hexagon rings, we have 6 carbon atoms, and these are the 6 pi electrons. So what we call, they form a pi electronic cloud, pi electronic cloud. So they are ready to really react with the other materials. And you can see here is this looks like is the electronic cloud of this carbon nanotube interacting with the graphene. And this is the overlap is pretty strong. So we always say, if I bring in a one graphene layer to say second graphene monolayer, make a bilayer system, or with another compound, this pi electronic interaction is going to be weaker than either ionic or covalent, which is in plane bonding. And this all depends on how flexible your electronic cloud is. So this is, you see in this literature, in graphene carbon nanotubes, is how strong your pi interaction is. So we can again summarize the bonding between these compounds. You can see here the linear change comes out to sp. The graphene is the sp2. And nanotubes again is sp2, but they have this curvature effect, so they are strained sp2 bonds. And if you look at the sp3, is interestingly is the diamond, which is pretty strong in terms of this in class of materials. Good. So it ends, I think, the first session on time. So open to questions, comments, and then we'll take a break.
Session is open now. Session is open now. If there are any doubts or wants any type of clarification, please you may contact to sir and write a question in your chat box too.
Please ask questions, because if you don't ask questions, then I do not know how I'm doing, And I'm here to explain things. I think this is a little drawback of the online thing, because stop sharing. Because in a classroom, when I give lectures, then I force them to ask questions. Good. So it's going to be a little complex. There's a lot of equations are coming up. So please have caffeine, dose of caffeine. And we'll meet in, 15 minutes? So we start at 11:45. Okay? Thank you. Yeah. Thanks, Ayushi. At least you are following me. Thank you, Dr. Naidu. Thank you. We'll see you in about 15 minutes. Okay. Start correct. Okay, so let's move to next 35 to 40 minutes or 45 minutes. Is going to be a short lecture because a lot of equations, and I really want you to go through the fundamentals of quantum mechanics. So please ask questions, kabhi bhi, because the concept is not easy, especially the other half who are engineers, engineering background, and so the key thing comes out is from classical mechanics and quantum mechanics is about the energy. And I want to again emphasize not the science students, participants, but the engineering. The beauty is at the quantum level, energy is not continuous. It becomes quantized. That's the key thing is. And I'll show you some of the examples, especially the Bohr's model. This is again is a grade 11, 12 physics. But I moved to called particle in a box, where you can see the energy distribution is not a continuous, but only the certain energy levels are allowed to make a transition of electron from one state to other state. So this is a simple, I call is a one particle system or one electron system. And once we move to nanoscale systems where we have a 10 to the power 23 atoms, then the quantum many-body system is going to be really complex, which I hope to do it in the afternoon. So famous model, the Bohr's model, again, is the inspiration came from planets, a planetary model, where we have a electron is sort of moving around in a fixed orbit around the nucleus. And you can see here this electron can rotate on certain states. The closer to nucleus is we call the n is equal to 1. So these are our quantum numbers, if you remember the principal quantum numbers. So n is equal to 1, and as you move further away from nucleus is n is equal to 2, or further n is equal to 3, and then so on. So it depends on the atom to atom. Is the hydrogen atom has only one electron. So definitely it's going to be at n is equal to 1 level. But if you move further in periodic table with a larger number of electrons or Z number, and then you have the electron rotating further away from nucleus. So what is the restriction first? This comes out is electrons are allowed to rotate on a certain state, not all the states. And this case is the hydrogen example. And so if you use a simple, the classical expression of a centripetal force, we find is, so forget about this constant, but you look at the force, mv square or r, where m is mass, v is velocity, and r is radius of this particle, is definitely related to the electronic charge and the radius. So using this, and then we impose this condition, we call the momentum condition, is RMV is equal to NH cross, where N is the principal quantum number, these the states, and H cross comes from, again, is the quantum mechanics called Planck's constant, reduced Planck's constant. And from there, you can calculate the radius of these circular orbits in terms of the mass, the electron, the Planck's constant. This is another constant, but you can see the relationship between Rn and n, which is n is equal to 1, 2, 3. So from there, you can calculate. I've missed. I'm not skipping the lot of steps in between, but what you can see, the energy En is a certain constant, 13.6 eV over 1 over n squared, where n is a principal quantum. And always make a note here, the negative sign represents the stability of the system. What we call system is bound if the energy is a negative. And if the energy becomes positive, we say system is unbound or not bound. And there are reasons to do it, which I will ask in your homework problem. So let's move to now Bohr's model to energy well. And rather, this is what we call is the lowest state of the energy is the ground state, which is energy n is equal to 1. And in our case, it's going to be a 13.6 eV. And I'm using the expression here. If n is equal to 1, energy simply becomes minus 13.6. And you can, from there, the ground state, and you can then determine n is equal to 2, 3, 4, and so on. So this sort of rises. So these what we refer as the excited state. So transition occurs because of the incident photon, then it picks up the electron, excites it. So this is again given by the difference in the energies of these states. So we have the transition state is n to n naught, where n naught is our ground state, n is one of the excited states. And from there, you can again, applying the quantum mechanical principle, energy is simply related to the Planck's constant, the velocity of light, and the wavelength, hc over lambda. So you can easily calculate the lambda, which is related to this transition state from the ground state to one of the excited states. And these numbers coming out of this lambda in these is consistent with what we observe in so-called the hydrogen line spectra. So this is really quite a successful application of Bohr's model, although it is a kind of a hybrid model. It sort of takes the constraint about the movement of electrons in certain orbits. So this is again another cartoon. As you can see here, is the energy basically is coming out from 13.6 to 2 to 3 to 4. And this jumping of electrons from one state to other sort of gives the lambda for our calculations. So there are pros and cons, as you know, for any model. That electron does have now the wave-like characteristics because we can have the energy in terms of the wavelength. We have also so-called this orbital angular momentum, which is again is a quantized. We have a discrete energy levels, and is really highly successful for hydrogen atoms, and there are certain number of calculations results which are proven to be very, very reliable and accurate. But again, as you know, any given model has a cons. The first thing is the restriction of having a circular orbits. And then as you move away from hydrogen atoms to say helium or other higher Z number atoms, then it sort of turns out to be not too reliable. And further on, it was shown that indeed it violates the uncertainty principle of delta P, which is a deviation in the momentum. Delta X is a displacement or the location of the position, which is about H cross, Heisenberg's uncertainty principle. But that's fine, is always remember is any model is not going to be the 100% reliable. It has to have a successful cases but it's going to have some drawbacks. So in our field, one should be aware of the drawbacks of a given model. So let's look at the application. And this is again, I'm just skipping a lot of mathematics and just showing is indeed, you can use this expression to look into so-called the quantum confinement effects. Means the smaller the radius of our nanoparticles, what's going to happen to the transition? Is there any relationship? So, again, I'm using this uncertainty principle. Delta P times delta X is H cross approximately. And then, so if I take my delta X to be 2R, where R is the radius of the quantum dot. From there, I can see delta P is going to be approximately H cross over 2R. So my energy is going to be, which is P squared 2M. This is again, we are talking about the quantum mechanics. And I substitute P as the delta P. And again, remember, this is just a back of the envelope calculation. We would like to know, is there any relationship between the energy of the transition and the radius of the quantum dot? From there, we can simply substitute delta P in terms of H cross over 2R. And what you can see here is indeed the energy is inversely proportional to R square, where R is our radius of the quantum dot. So from here, inversely proportional means is smaller the radius, the dot, or smaller the size of the dot, is going to have a higher transition energy. And you can see that experimentally, as we are talking about this so-called the core shell quantum dots, where we have the zinc cadmium sulfide as a shell and zinc sulfide as a core. And for these dots, they tend to have a smaller diameter. So you can see here there's a nicely, they are in a higher energy range, it's blue. But as we move down to some other dots, which has a higher radius, independent of the composition, you can see here the beauty of the argument, that all the compositions are varying from zinc sulfide, cadmium sulfide to cadmium selenide to cadmium zinc selenide, but the transition is governed by how big or how small the quantum dot is. So the higher diameter, larger diameter is going to be red, and small diameter is going to be blue. This nicely fits in these the back of the envelope calculation results based on quantum mechanics to explain the transitions in these zero-dimensional quantum dots. So let's move to now a little more complicated mathematics. We call is a particle in a box. And again, you can see we are picking up a very simplified description. We had 10 to the power 23 atoms. And again, number of electrons floating around in a solid, but we're picking up a single electron. And we assume the single electron is confined to a box which is represented by the periodic potential, which is coming from the nuclei to which electrons experiences in a solid. So this again refers to also what you call electron confined in an atom, or if you pick up a neutron confined in a nucleus. So these, the quantum mechanical particles, simply can be represented by a simple particle in a box. So what is happening is, and this is a beautiful example about looking at the classical versus the quantum difference. Classically, we keep the particle in a box, but it's going to sort of move around at the same energy state. It goes, hits the wall, comes back, hits the wall, comes back, depending on elastic or inelastic collisions. But quantum mechanically now, what we have is only not all the states, but only certain states are allowed. You can see here from B, if you go further down, which I'll show you later, states. So this sort of gives a quantum sort of a description. And this is a valid because my box size is very, very small. It's within the nanometer regime. So this picture holds definitely for larger systems. It's called a macroscopic world, like planets. But this sort of picture sort of holds for microscopic particles, which is we call the electrons, protons, and so on. So again, I'm going to emphasize is in quantum mechanical regime for a very, very small length scale, the particle is going to occupy only the certain energy levels, which means energy quantization occurs for quantum regime, not the classical regime. That's the key difference, energy quantization. So let's look at it. The boundary conditions. So I'm going to go slowly, hopefully, in the mathematical details. So we are looking at the potential because we had to define the box. Let me go to other slide. Where is it? Yeah. So this is the box we have. So what we define is electron in the box can be confined only if we have the higher barrier at the walls. So this electron cannot escape outside of this well. It needs to climb up in the wall to get into this side. But it has a very, very high energy. We call it infinite. And we keep our electron or particle to be at the zero energy. So this is a well, and these are the barriers. So this is a box picture. So if I look at here the cases A and B, and if I showed you here is the wall, which is the infinite potential, and I pick up a different length. So these are the different sort of states coming out from our n is equal to 1, 2, 3, 4. So what comes down to the wavelength, again, I'm skipping the mathematical details. This is the answer we can arrive at. Is the wavelength depends on the L, which is the length of the box, and the state, the N. And this is the momentum. Momentum is going to be simply NH, and is the number of states. H is a Planck's constant, and is the length of the box. And then energy is going to be is the N square of the nth level, H square over 8 ml square. So let's go back and see this is a little better improvement over the Bohr's model, where we have energy is simply a constant 13.6 over 1 over n square. But as you move from a simple Bohr's model to particle in a box, the energy has, again, a simple expression, but it has a depends now the brings in the mass of the particle and the Planck's with the L squared there. This gives is also the picture is energy indeed is quantized and is discrete eigen values appear depending on the n values. So let's bring into the famous equation in quantum mechanics. As you know, in classical mechanics, we have F is equal to ma in Newton's classical equation, which dictates the force versus acceleration or displacement, describes it. But in quantum mechanics, we have Schrodinger equation. And this is really one of the most fundamental equation. And if you can understand Schrodinger equation, I think you can do anything in your life. What does it tell us? It tells us is for the given case, let's focus on the wave function. So we're describing the particle's nature by the wave function. And wave function depends on my position coordinates. X is a position coordinate. So this term is simply in quantum mechanics called kinetic energy term. Okay. So energy is going to be the constant, the mass over a second differential d square by dx square of the wave function. So this gives us a kinetic energy, and this gives us the potential energy component, ux, where u is a potential energy. operating on psi x. And the left-hand side, if you solve it, it gives us the energy and psi x. So this is a simple, if you have one of you, I think, mathematicians, participants, they can see, aha, this is a simple differential equation, which can be solved easily if you know the parameter u. Because psi is chosen for our case. So second order differentiation gives the kinetic energy, and knowing the u, we can solve for the energy of the system. So the trick of the trade is what I call in simulation is given the wave function or the electron density, which is the square of the wave function. If you know it, you can calculate energy of the system. So always our objective is what is the minimum ground state energy of the system. And I'll tell you how to find the minimum, but we always calculate the energy knowing the psi x. The question now comes is kinetic energy is very simple, how to get the u. And we use a lot of approximations to get the estimate of u, not exact, but the estimate. It does satisfies energy conservation. You can see kinetic energy, potential energy is total energy. And I just described u is a ux. And solution is, of course, the psi x. And h cross is our Planck's constant. So if I look at it here, is u now is coming out that between 0 and L, this is our condition. So what we're trying to do now is we are trying to estimate what is u. We pick away the box. And this again is our constraints. You can pick up anything you want, but this is one of the, I call the simplest constraint. We can see the effect of it on the energy. So if you pick up the u to be 0 between inside the well, but infinite outside the well, and then go back and substitute into our Schrödinger equation. So what you find is indeed the wave function has a sine-like characteristics, sine wave, which depends on the length of the box and comes down to this quantum number, n. So this n basically defines the psi subscript n, which is a position dependent. This is the position dependent. And from there, you can infer to the momentum and the energy, which comes out to be the n square over L square. So I skipped the mathematics in terms of how to solve the equations, but this sort of important thing is the nature of the wave function comes out for n is equal to 1, 2, and 3, and so on. This is now we're looking at the probability because it's much easier to calculate the probability which is in the dashed line, which is the square of the wave function. And you can see the probability of electron in this well is going to be maximum at the center and then sort of comes down at the end of the box, because again, it reaches the end of the box, barrier is high, sort of it comes back. For the second state, n is equal to 2, now is not a ground state, but is an excited state. So it has the probability of occurring, you can see, not at the center, but displaced from the center. And you have further n is equal to 3, n is equal to 4. So you have different what we call the modes. And this is mathematically is true. One can easily see because it's a simple analytical equation. One can solve it exactly. So this is going to be the last slide. Which goes from the Bose model to a simple one electron model. And now is we call it nanoscale systems, which has again a number of electrons, number of atoms. So please always remember is exact determination is impossible for these many electron systems. and because of the nature of the U, the way we estimate or we provide the input for the U. So what has happened in the last 30, 35 years is uh, the people, the research scientists have come up with a lot of models. And the key thing is the various level of approximations, which turn out to be is pretty good. I mean, they are not an easy, simple approximations, but they do have this predictive capability. But always remember, these are the approximations, not the exact determination. That's the key thing. So whenever you see a results coming off the simulation or a model, please always look into the level of approximation being used to determine the properties. And being experimentalist, you can sort of judge how good the prediction is. So this is, I showed you earlier, is the trick of the trade is to calculate the total energy of the system, which I'll tell you more in afternoon talk. So what we have, you can see, is the cluster interacting with a molecule. And what we are doing here is we are calculating the total energy of this conjugated system at different distances. So you go far, when the distance is pretty large, about 5 angstrom, you can see the energy is almost zero. Now, as you bring in, you plot it, you can see at certain point, energy has a minimum and then rises because of it's too close. The Pauli's exclusion repulsion principle sort of takes over and energy rises. So what we say is this is the lowest energy of the system, when the active site is a nitrogen site. If you look at the other side, the right, the top side, is a slightly lower energy related to the N side. And if I bring in so-called the oxygen side, is definitely is the way up. So what we do in to understand is which of the sites is going to be active and which of the site is going to provide the most stable system. And come out from this thing is indeed the action occurs at the top side, not either N site or O site. So now you can see here, you do experiment, you have the cluster, you have the molecule, you form a conjugated system, but you don't know exactly what are the atomistic details of this interaction is. And so simulation sort of comes in and provides really a complementary picture, assisting the experimentalist. That we can tell the experimentalist, indeed, you have the stable system, but the stable system is formed by interaction governed by the top side. And you can see from here is, depending on the site interaction, you are going to have different properties of the conjugated system. So this really matches very well. I call it a very, very good marriage between experiment and theory to understand the fundamental processes of at the atomistic level. That's the key thing here, at the nano level for a given system. So let me stop here. And we have, how many minutes now we have? There's another 30 minutes. So we have half an hour to either eat lunch or ask questions. I'm here, open to floor.
You may write questions in the chat box.
Or anything you would like to ask, because you have this opportunity to jump in. And if I don't have the answer, I will look into it and come back to you either today or tomorrow.
Now, this is the time for group photograph. I request all the participants, please start their video so that we can take a photograph.
But you can see my aim is here, knowing the diverse audience. I didn't want you to get into the details of mathematics, because I had taken definitely more than an hour to show you. But my idea is to sort of introduce the topics. And if you're interested, either approach to me or look at the books, or talk to other experts, and you can really get into the quantum mechanics. Any questions, Ms. Dubey? Dr. Ahi, being a civil engineer, I realized I had to go very slow. Any questions about quantum mechanics? Miss Savita? We have more people today than yesterday. Two new. Who are they? Garima, can you? Yesterday we had a session where we asked the participants to talk about themselves. Can you tell us what's your background and what you would like to get it from this course? Where is Garima? Here, I cannot see her. Garima Tiwari. Miss Tiwari? Who else? The second one? Mr. Sudeep, Dr. Sudeep. He's not there? I don't know if she's on or not. Not there, yeah. This is what happens with the online thing, and I turn it on and do it. You want to take the photographs? Dr. Natarajan, any questions? I think Miss Loveleen is also new, isn't it? Yesterday I didn't see her name. Yesterday she was there. Did she talk about? I think we are done early, so that's why they are not coming.
म्यूट करता
3:15 tutorial session. 3:15 tutorial session.
No. We have what is 2 o'clock? We have 3 lectures today.
So we'll join by, sir, 2 o'clock, is it? Or before that? It's 12:20.
Yeah, so
Another 15 minutes break.
No. You ordered it now, or I think let's wait, follow the schedule. 2 p.m.
2 p.m.
Yeah. She's from physics, yeah? Hello, Aishi. It's too simple for you? They're doing something else. It is not too simple. I thought you're from physics. But there's a question I think came in. Yeah, how do I go to my chat box? Chat. No, Aishi, quantum is fun. And as I said, if you can do Schrodinger equation, you can do anything in your life. So it's little mathematics, but once you know, especially particle in a box problem, and nowadays we have a lot of simulation package, which you don't have to know about the quantum mechanics. So whole idea is what I'm trying to show, how to do the analysis of these computer codes. So you have to know about a little bit about the background, exactly what is going on. And there's a question from Dr. Nelsa. So always remember is when we make a graphene, graphene is going to be defective, is going to be impure, and not pure graphene. So what's the push is coming from the community is, let's take the graphene oxide and see if we can refine the properties of graphene oxide for energy storage applications. I'll pick up a few examples in later. So ideally, graphene is the best. And as you know, is a fast mobility. Electron mobility is very, very high. So photon comes in, electron hole generates it, and electron zip through the system. And that's what you want. But it's not easy to make pristine or pure graphene. So people are, in practicality, they are moving towards graphene oxide. So it depends on case to case. Does that answer your question? Yes, Aishi, you wait till third lecture, we can talk about more quantum mechanics. Thank you, Dr. Nisa. Okay, so let's take picture and then we close the session because they can do other things. Everyone's busy nowadays. Lilia, good. Take care.
Thank you.
So what I realized is
you ever feel like you're being
Okay. Start. Go. So, welcome back again. Let's look into now, I call a hardcore theory part. And hopefully I'm not going to bore you. Did it come out? So what we learned so far is that in nano scale regime, we take advantage of the principles of quantum mechanics and find that energy is quantized coming from the simple model of Bohr's model of a hydrogen atom or a particle in a box. But the question comes down to the nanoscale systems, which are quantum many-body systems. And hopefully in about the next 30 to 35 minutes, I'll not go into details about the mathematics, but conceptually, I can show you is how can we deal with these systems. Of course, we need to use some approximations, which I'll describe, and then show you some results, hopefully in the next 2 days. So I just said earlier, this morning is for these many-body systems, is exact determination is not possible. So one has to use sort of a different level of approximation to solve these many-body problem. And surprisingly, these approximations do yield very good, reliable and accurate results about structural and electronic properties of materials, which are helpful in applying them for energy-related applications. So yesterday we went through a crystalline solid, and the key signature of a crystalline solid is a periodicity. Then we introduced the mathematical concepts, real versus case space, and which is helpful in looking into the X-ray diffraction. So before I go, I just want to share this called quantum length scale, which we are going to do a lot of crystalline properties. And what do they mean in terms of the length scale? And that's it's a very useful sort of information. One should be aware of it so that once we analyze our results, we know where we are. So whenever we talk about electronic transport, we're talking about the Fermi wavelength, which is the order of 10th of nanometer, and the scattering length of these electrons when they go through the lattice, it tends to be about the 10 to 100 nanometers. And when we move to thermal transport, then we do not have electron, but so-called the phonons, the lattice vibration, mean free path is about 100 nanometers at room temperature. And as you go, the higher temperature is going to get smaller and smaller because the vibrations are going to be larger and larger. Then we have a so-called optical or a magnetic interaction with the material. So when you talk about optical interaction, the photons, incoming photons, as we know, is about the 100 to 300 nanometer length scale, because light wavelength in the medium is lambda over 2n, where n is the refractive index of the material. And when we talk about magnetic interaction, we have it's called a short range. It's an exchange interaction between the spins. which is about 110 to 10 nanometers. But we do have a long range, so-called a dipole-dipole interaction, which is really well beyond micron scale. So this is a sort of a useful slide to be aware of the properties and what kind of length scale we're talking about. So I think I showed this slide yesterday we're talking about an crystalline solid. So we have a large number of atoms and a small volume. And so we need to exploit the fact that these atoms are really arranged in a regular pattern, called periodical pattern. Periodicity is the characteristic of a crystalline solid. So let's come down to now wave function. And if you have such a large number of atoms, and I think I gave you a little bit sort of glimpse about this wave function, especially when you look at the probability, it has the measurable information, which is the psi star. And then also it depends on the location or position of electrons and nuclei, which is sort of a factorial scaling is there. So if you use this factorial scaling as a sort of estimated guess, we take the carbon atom, which is 6 electrons, we are going to have about 6 factorial evaluation, about 720. But as you go further down from carbon, oxygen, and a neon, you're talking about such a small system, 10 electrons, we have such a large number of evaluations. And if you go to a molecule, not yet the crystal, then we have about 30 electrons, because 2 oxygens and silicon and 3 nuclei. And this gives us such an enormous number of evaluations. So in this sense, it's unpractical to solve the system exactly. That's a sort of a message that's coming out. Simply, we cannot do it. So how do we do it? And as I said, is we need to exploit the periodicity. And the fact is if this is the case, then we use this translation symmetry. There's a famous theorem called Bloch theorem, which permits to go from infinite matrices to infinite number of finite matrices with size equal to the number of basis functions in itself. So look at the key thing here is, so if you look at the exact sort of case on the left hand, we have infinite matrices to solve. But by applying this translation symmetry using a Bloch theorem, what we simply reducing the size to infinite number of finite matrices. That's the thing. And evaluation of a finite matrices, although they are a large number, is quite possible. That's the key thing is coming out of the periodicity. But the key thing also is we have to make sure, because we are employing this translation of periodicity to solve the problem, but what are the perturbation we provide to the crystal? It's either electric, optical, or magnetic. It has to be a small perturbation because we need to preserve this translation symmetry. And if we cannot preserve it, then this sort of Bloch theorem fails. We cannot exploit the Bloch theorem. So translation symmetry, we need to preserve it, and it helps to reduce a infinite problem to finite number times finite problem times infinite evaluations. So that's the message here. So let's look at the quartz crystal and then see how can we simulate it. So you have a quartz crystal means SiO4. We have oxygen atoms, so it's tetrahedral coordinate with the silicon. And if you form this structure, it looks like this structure. So we go from a crystal structure to simulation where we have the periodicity of the crystalline lattice. And every unit is basically made of SiO4 molecule. Then what we do is we take, so this is a crystal information. Now the overlap with the lattice, which is a mathematical concept. So we have the atomic information about the coordinates and the atoms, but we overlap with the lattice, which is a mathematical concept, which provides us to a means to evaluate the problem or look at the answers. So the infinite crystal definitely can be generated by two atoms with the application of symmetry operation, which we sort of impose on the crystalline structure. So this is the lattice. You can see here, and then it's converted to the points. And that's why we have is so-called the unit cell, which has a A1 and A2 giving to this SI or two units. So infinite crystal can definitely be simulated by simply a small unit cell and applying the periodic condition we then generate. So the problem becomes really tractable as when can use it. And then applying this even to different combinations, you can definitely generate the different lattice signs. So this is basically simple, the product of the translation symmetry operations. And that's how group theory comes in to understand it. So we talk about the periodicity now. What does it do? We do have the background nuclei. And what do they do? They provide so-called the attractive potential to these electrons. But this potential is not a uniform potential. You can see there is a variation. And this variation in potential, what it does is it basically introduces the gap between these free electron states. If you look at here without a potential, lattice potential, electron can go anywhere. It's a very, very nice continuous state. But once we introduce the lattice potential, which is again is being varied, we have these gaps. And these energy gaps then are related to so-called the band gap of the material, which in turn is related to the absorption of light, how efficient our material is to absorb the solar light to convert into electricity. So basically solar cell formation. And this is, we talked about it yesterday also, is in a sense, the gap states are basically dictated by the valence electron because the core states has hardly any dispersion, and the valence electron basically provides this the splitting of the bands, giving us the gaps. So let's come to the block theorem. So I'm not going to prove it, but to tell you what exactly states. So we are talking about, the key thing is here is our potential VR is periodic. So VR is a function of R, and the capital R, the uppercase R is the lattice factor, which is combination of the A1, A2, A3. And these are the lattice vectors which is seen before. A1 and A2 in this 2D, and A3 comes perpendicular to the plane. So this is termed as a lattice vector. And then N1, N2, N3 are the integer values, 1, 2, 3, 4. So the V being periodic, what we do is we can then write the wave function, which is psi r in terms of a phase factor, E I equals to R times UKR. And this UKR, as you can see, is a periodic. That's the condition we are imposing. So because of the periodic conditions, what you see here is we have a index called psi k, and it represents the state, eigenstate of the system, which can go from 1 to infinity. So we start with this our free electron wave function, psi k of the function of the position r is E I k to the r UKR. The UK is a periodic, and this is a phase factor provided. And different k values, you can see here, because again, is being ik dot r means this psi k is a complex function. So what we can do, we can have a real part or imaginary part. And we are mostly interested in the real part, what's going on. So the upper graph, you can see here, this perfect sine wave, the real, and imaginary sort of is going to be displayed appearing like this. For lambda, which is defined by 2 pi over this wave vector k. So if I choose k is equal to be 0, you can see here is we have the wave function as a maximum at the nuclei, then goes down and maximum. That's a periodic. And if I look at the K, it's going to non-zero. And then, so it sort of has this again oscillations, goes down, and you can see the dotted line showing the sine wave on this thing. And similarly, we can do K is equal to pi over A. So you have this again, the maximum going up and down for the wave function. So this sort of gives you a pictorial representation of the wave function at a different K point, which is a wave vector induced by the Bloch theorem, and comes down to periodicity. So this is again, as we are talking about, is a 1D band structure. So if I look at the energy, which is simply h square k square over 2m, you have a nice parabola. There's a continuous parabola where energy was plotted with k. But once we induce the periodic potential, what we have is we have the set of parabolas. You can see the crossing each other. So this is at, say, pi over a, 2 pi over a, and so on. So if we use this folding, what we call reduced Jones scheme, to represent the effect of periodic potential on our free electron E versus K curve, you can clearly see is the gaps show up for different energy levels, E1, E2, E3, at the boundary zone pi over A. And this is what we call is the introduction of the band gap due to the periodic potential in the electron E versus K dispersion curve. So now we have two quantum numbers. If you remember the Bohr's model or the particle box, we have one quantum number n, showing the eigenstate 1, 2, 3. But the periodicity or the K space sort of induces another quantum number. So eigenvalues are going to be En function of K. So this is the difference between a free electron system and electron in a crystal that is defined by two quantum numbers. This again is sort of a pictorial. You can see what happens if you go from atom, very discrete states, 1s, 2s, 2p, we form a molecule. And then we have again little broadening of these states because of the overlap wave function. And if you go solid, then definitely we are going to have the bands showing up, coming out of these, the atoms consisting of these 1s, 2s, 2p states. And the same thing is repeated here. You can see from distance versus energy curve, you far apart, you have the two discrete sort of states. And once you bring in together to form a solid, you're going to have a sort of a broadening of the levels and then splitting to so-called the valence states and the conduction states. And then you have a gap. So let's go to now is a little bit in mathematics, and I'm going to show you some equations. This is what we talked yesterday about the Brilliant Zone, and I think one of the problems, the homework problem, was related to it. And what you can see is as we apply the Fourier transformation, we can go from our real space or direct lattice of the unit cell of this FCC crystal to the Brilliant Zone in the K space for a FCC lattice. So whenever we solve these periodic equations or simulations, we always do the K space because of the transformation of the application of the Bloch theorem, applying the periodic boundary conditions. And always remember, I talked about these. When first time I saw these Greek labels, I was kind of a little confused, but then realized is that these are so-called the special points, the high symmetry points. And they are labeled in letters, which gamma is always is a sort of a symmetry, center of the symmetry 0, 0, 0. And depends on how you go along the axis or through the plane, you have X, K, or M points. And always remember this, the Brilliant Zone or the K points, it depends on the symmetry of the crystal, not the composition of the crystal. Because if you remember what we did, we had the crystal and we sort of overlapped with the lattice, and this defines into the 14 types of crystalline lattices. So that's a mathematical concept. irrespective of the composition of the crystal. So this is going to be the same brilliance zone for, say, magnesium oxide, which is a rock solid structure, or sodium chloride, or lithium fluoride. Although the details of band structure depends on the composition. So this is again let's have some patience and go through this slide, which tells you is how do we start? Is that we start with the crystal as a macroscopic, and remember, there's a finite array of large number of atoms. Of course, it's going to have surface, but the surface is going to be very, very small. So the real crystal exhibits a bulk-like features and properties. So this is a macroscopic finite array. Then we bring in macro lattice because we have to overlap with the crystalline material. So macro lattice is n unit cells. And in order to have a smaller surface, of course, it's going to be large so that the surface effects are negligible. And then we apply the periodic boundary condition with the A1, A2, A3, which are the lattice vectors, the lattice constants. Then we can definitely have our model which provides us a perfect crystal and overlapping with the crystallographic model of infinite array of cells containing the same group of atoms. So that's the key thing is a marriage of your materials with the mathematical concept of lattice. This again is a pictorial. You can see that we have infinite number arrays of sort of these grids. And as you start applying the atoms, placing them, you form your crystalline structure. And then it's coming from the group theory that you can have this cumulative group of n, and then applying the translation operator, you generate the crystal structure. So if we do what are the block functions are? And like I said earlier, if we start with a local basis where we have the atomic orbitals and we apply the periodic boundary conditions, what we have is the function, which is position dependent, now has a position as well as the k dependence. That's the key difference here between a local basis and a so-called the block basis. And then, of course, you can describe the block basis in terms of some exponential factor, which further can also define it. So this sort of provides a complete picture of the block function representing the electrons in a given solid. I don't want to go into details about the notations, but that sort of tells you the picture is really complex. It's not simple as it sounds to be. So this again sort of gives you a pictorial description, is going from the atomic basis. So once you have the block function basis, you have a perfect diagonalization where n blocks of size m associate with the km. So remember we talked about infinite arrays to infinite number of finite arrays. That's here the advantage we have because of the periodic conditions. So some results. If I look at the band structure of a quartz, is SiO2, we talked about it. So what we have is the energy, and then you have the brilliance zone path. So these are the spatial high symmetry points, gamma, A, H, K, gamma, M, L. And from here you can see, from gamma you can go to direction to map out the dispersion of these eigenstates. So if I look at the big picture, you have a very, very deep, the 1s state associated with the silicon. As you know, silicon has a larger core, is 14 electrons. So it sits in the deep. And if compared to oxygen, which has only 8 electrons, the 1s sits way up here. And you can define the 2s, 2p, and so on. If you zoom in these states, which are defined up at the top, you can see here, then we have the real is we call a spaghetti. So you have the states of oxygen S, silicon P, and oxygen P. So this state at 0 is called top of the valence band. An insulator we defined as a Fermi energy. So this occupied level, if you further zoom in, you can see is top of the valence band. How does it look like? And this is our conduction band, the unoccupied states where the electrons are not occupied. So when we shine the light, the transition of electron occurs from the valence band to the conduction band. And in order to occur this transition, remember the gap. The electron has to cross the gap. Means the photon, incoming photon, should have the value equal to this gap, so the electron can move from valence to conduction band. So this gap, in a sense, defines the absorption characteristic of materials for a given photon. If photon energy is less than the gap, simply is not going to get absorbed. And the material is not going to be a good photovoltaic material, because we need a good absorption of light, visible light especially. We look into the silicon is another example. As we know, the 14 electrons are in silicon. So we have so-called the valence band of 2s2, 2p2, 3s2, 3p2. So 1s2, 2s2, 2p2. So it should be 2p6, the typo here. As we call the core states, and these are the valence states. And the unoccupied or conduction band, of course, will be 3d, 4s, and 4p, so on. So you can see from here, is if I look at the billion zone K points with the energy, you can really map out what exactly the dispersion of the states which are occupied by electrons or unoccupied states, referring to valence band or conduction band. So really you can calculate the electronic properties of material with high accuracy and giving a really good picture what happens in a solid. So once we have it, you can see, you can calculate anything you want. So requirement is the good energy or the good basis function or good electron density. And once you have it, you can go to either electronic, again, as you can see the transistors, or optical, or mechanical, even a magnetism and thermal properties. So what we say is anything is possible once we know how good our density, electron density, to describe the material. So let's look at the method. What do we do? And as you can see here, from going from atom to cluster of atoms to solid state, the number of electrons, of course, is increasing. So we have a many-body problem. And like we talked about, the fundamental equation we need to solve, which is defined by a Hamiltonian. And you can see the wave function, then is equal to energy operated on wave function. So we call H psi is equal to E psi. And the wave function you can see has the coordinate is the electronic coordinate. Of course, is with reference to the nuclei coordinate. So the question is now you have to define what is our Hamiltonian is. And as we did before is we had to have the kinetic energy contribution. And this is called potential energy. If you remember, our energy is h cross square by 2m times second derivative of a wave function with respect to r. We define kinetic energy and then u. So in this case now we can write is electron kinetic energy, nuclei kinetic energy. Then we have the potential energy is electron, nuclei, and electron nuclei. So three components. And then we have another factor, what we call external potential, which you would like to have the external perturbation to the system. So you can see here is we have now electron and nuclei. Again, it says problem is complex. So can we use a simple fact that nuclei in a given atom, nuclei are much heavier than electrons. Okay. So electronic motion is much faster than nuclei motion. So in the first approximation, a first step, what we can say, we can decouple electronic motion to nuclei motion. So what we say is that my electrons are floating around in a given atom on a constant potential given by the nuclei. So in a sense, when you decouple it, the problem becomes much simpler, attractable. So this is called the Born-Oppenheimer approximation. And what it does is you can see here from right, the cartoon, here is we have the electrons, nucleus, and external potential. By decoupling electron nucleus, we say the electrons are moving in a fixed nucleus, in a uniform potential. So that helps to sort of ignore or approximate the terms which are related to nuclei. So we can say Tn, kinetic energy term, the potential energy term nuclei, electron nuclei can be sort of taken away, and our Hamiltonian simply becomes the kinetic energy of electron, the electron-electron interaction energy, and the perturbation potential. You can see the simplicity is coming out. Now is when you're talking about the electron we have to take account of the electronic property, which is electrons are, if you remember, is fermions. We have two types of particles called bosons and fermions. So electrons of fermions means the exchange of the spin does matter. So what you have is here, we need to add this term because of the quantum mechanical nature of the electrons called exchange correlation potential. And thus I'll show you how to estimate this VXC. So our Hamiltonian, if you remember, H psi is equal to E psi, has the term now kinetic energy of electron-electron interaction energy, external potential, and this term exchange correlation potential, which gives you the E. So that's fine. We decoupled the Hamiltonian from electron to nuclei. What about the wave function? So you can see here, the wave function or psi is a many-body function, many-electron function. Means it's a function of the n number of electrons. So from simplicity, what we can say is this wave function of n electrons can be written as the product of the wave function of every electron. But it's not true, which we'll see how can we do it. But this is called the approximation from many electron wave function to single electron or single particle wave function. So the two approximations we are going to use is a Born-Oppenheimer approximation, which decouples an electron nuclei. And then we have the many-body function to single particle function. So then we have is called Hartree function, the Hartree approximation. So what Hartree came up with the idea is if we have this electronic wave function representing the electrons in a given solid, and they're all interacting. Let's assume this interaction to be very, very weak. So what we have is simply the independent particles, and they are moving in an effective background potential. So if we use this approximation or this idea, then simply we can transfer this many electron wave function to single product of single electron wave functions. And that helps. Because remember, here we're talking about 10 to the power 23 atoms in a solid. So this Coulombic repulsion between electron I, because you take care of it, and this electron I is moving in an effective potential by averaging out all the other electrons. So we have electron is interacting with the charge density distribution of the other electrons. It is called mean field approximation. So we can easily calculate this thing and term as a V Hartree. So V Hartree does is basically let us write the many body function to product of a single body functions. So far, so good. So we have Born-Oppenheimer approximation, which provides the decoupling of electron nuclei. We have Hartree approximation, which goes from n body to single body. But what about the nature of electrons, which are fermions? Means we have to have the anti-symmetric nature of the wave function. So the Fock comes in, and he sort of provides this exchange correlation idea. Go slow here is, so what we have is the two electrons, P and Q. Okay, if they do not transfer. So what happens is here, because they are in two different states, there's going to be a suppression of electron Coulomb energy because they are far apart. But the gain is so-called the exchange energy. And if the transfer occurs, means it comes closer to it, so there is no suppression of electron Coulomb energy, but there is no exchange energy because they are in the same state. Okay. So the Fock approximation kicks in. The two electrons at the same spin interchange position, means if in the same state, phi must change sign, going from up to down. Remember the Pauli's exclusion principles. No two electrons can have a same spin state. So this is called the exchange property. And what does it? It lowers the energy. So now let me show you some equations to give an idea of how complex the process is. So if we write the Hamiltonian instead of the so-called the kinetic energy term, this is the nuclear electron-electron interaction, electron-nuclei interaction, nuclei-nuclei, nuclei-electron. Then we solve the Schrödinger equation. When we apply the Oppenheimer, we take care of the electron-nuclei decoupling, so it becomes a less complex equation compared to the previous one. Then we apply the Fock approximation, which sort of relies on the Pauli's exclusion principle. So we have the many-body wave function becomes a product of we call Slater's determinant. That's a common technology we use. So once we have the Hamiltonian, we have the wave function. We use so-called this variational approach, which tells us that take the derivative of the energy, which is a psi in a Bra-Ket formation, with respect to the wave function, it has to be close to zero. So this condition, mathematical condition, makes sure that we have the minimum ground energy state, which is called the ground state of a system. And that's a trick of the trade, which depends on how you describe your wave function. But Hamiltonian is already given for the system. So then again once you apply the basis set, so this we had to apply for this condition, you have called Fock operator. And then we apply the basis set. This becomes the Ruth and Hall equations, which is solvable on computers. So the mathematical equation turns to this Ruth and Hall equations so that we can really calculate the numbers out of these approximations. So once we have the solution, what we have the two subspace, which is a Fock space, we call it. One is the spanned by the solution set and the space outside it. Because you can have, again, the infinite number of solutions here, equations for a given case. So one is between the solution set and one is outside it. So what we term is within the Fock space is called occupied orbit. And out of Fock space we call is a virtual orbit. So in summary, in this Hartree-Fock method is when you solve the equation, each electron sees the average potential due to other electrons and is independent of the other electrons. So far so good, because we can solve the equation. But it also has a con factor because it does not take care of the electron-electron correlation. How does electron sees this electron and modifies its motion? So in a Hartree-Fock method, simply it ignores electron correlation. So we move step one forward. That Hartree-Fock method is good in a sense it provides, it's called the exact exchange taking care of the Pauli's equivalent principle. But it doesn't care about the correlation movement in a solid because we have a large number of electrons. So comes to a next version of the theory called density functional theory. And I don't want you to go through the theorems because, again, these are mathematical theorems. But what they state, the key thing here is any external potential is a function of the electron density. Remember, here in Hartree-Fock space, we are talking about the wave function, not the density. In density functional theory, now they move to density, which is the square of the amplitude of the wave function. It's a probability density, we call it. And then what we do is we calculate the energy of the system with respect to the density and try to minimize it to make sure it's zero. So this is a pictorial thing, as you can have the real system, but the real system we have to move to called non-interacting system. This is our mean field approximation. But the advantage is the both systems is going to have same electron density. Means they're going to have same ground state properties. That's little advantages over the Hartree-Fock approximation, which deals with the wave function. So we have to solve only what we call the easier problem. So how do we do it? So we have this call is not the single particle, but because the Kohn-Sham theorem, we call Kohn-Sham particles. So our many-body electron function is now a non-interaction system, can be written as a product of the single particle functions. But we use the electron density, which is the square of the wave function. That's the difference here. So our Hartree-Fock equation simply becomes a so-called Kohn-Sham equation, where you can see the same sort of a Hamiltonian is going to be there. But the difference is now we are using a phi r, which is related to the electron density nr. For the case of, so this is our kinetic energy, and this is our effective potential is external, the Hartree potential electron-electron, and exchange correlation, which is unknown. So what it does is this DFT, density functional theory, sort of approximates the exchange correlation function in this fashion. And that depending on the level of approximation, we call LDA, GGA, or hybrid. So what we know, the equation is exact, but this functional form is unknown. So the approximation in DFT kicks in is called exchange correlation. So the first one is called local density approximation. And what it does, it assumes here. So you look at the density, this is density with respect to the location. So for exchange correlation function, you can see the density is taken to be uniform. Although there is a variation, but we pick up the uniform density. This refers to called local density approximation. It assumes electron gas is homogeneous locally. So our functional depends on the local electron density. But we know this is not correct because there is a gradient here. So what it comes down to next level of approximation called GGA, generalized gradient approximation, which does include corrections to this gradient nature of the electron density and becomes what they call non-local uniform electron gas. And then you can easily solve under the GGA approximation. So always remember is the development is incremental steps. The Born-Oppenheimer approximation, electron-nuclide decoupling. Then we have Hartree approximation, many-body wave function to single particle wave function. Then Fock kicks in, provides the exchange, sort of a evaluation of exchange, but ignores correlation. So DFT comes in, and now DFT talks about not the wave function, but let's take the electron density, which is observable. But it starts with the approximation called LDA. That's the uniform electron gas. And then you have a GGA, which improves the approximation to have the non-locally uniform electron gas. So that's this improvement in these approximation levels, which also helps to get the accurate and reliable results. So this is the way one sort of uses or the calculation called the black box. We have a lot of software packages, both free and you can buy it. And this, let me go through quickly. So we start with a guess our electron density. And so I pick up, say, we have a magnesium oxide, the crystal. I want to calculate it. So what I say, I take the magnesium atom and oxygen atom. That's my original guess as electron density. Then I calculate the effective potential, from solve the Cornsham equation to get the wave function. And from the wave function, we calculate the total energy. And we go the iterative process. So the idea is we have to minimize the total energy. And if the energy is minimized to a certain criteria, then we say calculation is converged. And then you go on, you calculate the force, then again see if it's converged, and certain criteria fulfilling it. So what we have in the end is a really very good value of energy and the electron density. And once you have it, you can do anything you would like to do. That's the key thing. So this slide shows you the over the years about the reliability of these calculations. So always remember, we are solving a numerical equation using some basis function. So we have a two parameter, it's called precision, which simply comes from how good your calculation is. And the accuracy when you compare your results with the experiment. So experimental part is here, which is provide the accuracy. And here the lattice constant of silicon, bulk. And over the years, you can see the precision is still sort of fluctuating. And now finally is approaching to this point, which is still far away from the experimental value. So, but if you look at the difference here, we are talking about difference about 1/100 or 4/100 of angstrom. So calculations have become very, very accurate in terms of providing the structural properties of a given material. And this is a slide I would like to show. This is one of my first work that came out. And what we are trying to understand is what is the effect of this periodic potential. on the atomic wave function. So we picked up the oxygen ion, and you can see here, this is the free ion coming out. And once we put this free ion in a crystalline lattice of magnesium oxide, you can see indeed the dotted line you can see is there is a significant distortion or a modification in the wave function of oxygen 2 minus. It becomes a little more broader related to the free ion value. So the message is the effect of crystalline periodic potential is indeed measurable, although it's not very, very significant, but is significant enough to sort of modify the electron density of a crystalline oxygen in a crystalline environment, which then affects the different properties. So I think this is the last slide. It's easier to handle the system. At least you can do the calculations on your laptop. The density is, you can observe it. And the big sort of advantage is reduces the problem, what we call dimensionality, so that we can run these calculations on a smaller computing machines. Thank you. Questions, comments?
For any doubts or clarification, you may write your queries in chat box.
All are sleeping? I guarantee you tomorrow's talk is going to be more relevant to materials. Oh, there is a question? Bhakti has a question today.
They are waiting for some homework slides, sir. I think so.
Homework slide. I have to did I share it with you? I'll share it.
Okay, sir. Sir, how to learn DFT?
That's a good question, Dr. Somesh. I use at this age prefer to say, let's use the black box approach. So if you can get hold of any DFT package or send me an email, or tomorrow I'll give you some addresses. You can do a screenshot, we can mail you. So these are the packages you can freely available. So only thing is either you have to know or you find a student who can install these software packages on your laptop or any other machine. And then from there, you start running a simple test calculations. So idea is you can run the code, see some results which you know, then you further go down to theoretical aspect. And the key aspect nowadays in DFT is to understand the use of exchange correlation potential. It defines LDA, GGA, hybrid, and so on. So that's a sort of an incremental approach, starting from black box and then going slowly deep into the theory. And tomorrow, definitely, I'll show you some of the software packages. Yogesh, again, is what kind of experiment you're doing is, I bet is going to be the structural, electronic, optical, or magnetic. So you do some measurements, like I was showing one experiment that people had done to see the manganese nanoparticle interacting with a molecule. But they don't know how the interaction is going through compared to, say, silver. So what we did is calculations, look at the charge density at the interface and say, aha, manganese is PD compared to silver, which is ST. So DFT is providing a sort of complementary tool to understand your experimental results. And not tomorrow, but the day after tomorrow, on day 4, I'll show you some of the results which we had done in our group to help understanding the experimental results.
Sir,
Is it okay, Yogesh?
Sir, is there any free software available for DFT?
Yes, there are a lot of free software. Tomorrow, I'll get you the link.
Okay, sir.
Okay, we'll do it.
And also suggest, sir, what type of understanding is required to understand properly the DFT calculation?
The understanding is, I prefer is use the black box approach. First, see, can you run your, first thing, install the software. Second thing, can you run the software on the model systems like magnesium oxide? Calculate the structural property, the electronic band structure, optical properties. And once you know, then you can use your own materials which you'd like to do it. So it's about, in a time, I should say 6 months, and you're going to be trained. I can also connect you to a lot of different collaborative groups in India, depending on your location. You can go and spend time for a week or months to understand, and you go back.
Okay, thank you, sir.
And time to time, I bring in my colleagues with me, and we offer weekly workshops in different places. So we'll let you know if you offer such a case. Okay?
Okay, sir.
These are okay, WhatsApp messages, or where are they? Oh, it's coming here.
Chat box, sir.
DWG drawings are often worked on by many professionals.
So I can share the homework?
Definitely, sir.
Let me show you the homework, and then I am done for the day. And Dr. Singh is going to send you the homework, but let me share it. So basically, it sort of gives you some idea about STM versus AFM, which has a tunneling current versus the force displacement curve. So just a 1 or 2 lines, if you can understand and write it. This is again a simple expression, and I talked about the chemical bond can be represented by the harmonic oscillator, the spring constant of harmonic oscillator defines the strength of the bond. So what kind of expression the energy states of these oscillators are going to have? And this model we use to understand the phonons or vibrational modes of a crystalline material. So that helps. It's similar to what we had done in a particle in a box. And this is you can say right away, number 3 is very simple, that if we have a graphene, but if a carbon atom is interacting with graphene, what kind of form is going to form? Is either sp, sp2 or sp3. So it should not take more than 6 minutes to do this homework. Is it okay? But you're going to share on WhatsApp and email. Okay? So any questions about homework? If not, if you need a little more difficult one, I can give you also. But it's your call.
I think there is no further question, sir.
So good. So it's 3:30, I think. Oh, sorry.
3:15, sir.
3:15.
3:20 around, we'll start the next session, sir.
3 o'clock, yeah. So it's good. 1 hour.
Ji.
Good. So it's going to be tutorial from 3:15
3:15.
on
XRD analysis 2.
XRD. So I'll see you tomorrow. And we'll definitely get into.
Is there any limitations of DFT, sir? There is a question by
yes.
Shikha
Dr.
Naidu.
Naidu is a very good question. And as you know, I talked about, let me show you the slide. So you can see the slide here. We're talking about the non-interacting system having a electron density similar to real system, which means we're talking about only the ground state properties. So as long as we talk about a ground state of a material, which is the structural property and the electronic property. But as we move to sort of optical transitions, so what we have is a ground state and excited state. But by definition, the density is a ground state density. So limitation of DFT is basically to describe the optical transitions. But now we have different tools to sort of modify or to improve on this limitation and to calculate the accurate optical properties. That makes sense? Yeah, Dr. Naidu, I'll give you tomorrow the list of software packages, and Dr. Singh, Bhavna Singh will also send you by WhatsApp and an email. So let me get the names and the website addresses. Okay, we'll do it tomorrow.
Thank you very much, sir, for today's session.
See you tomorrow then.
The next session will be start by 3:15, and tomorrow's session will start by 10:30 sharp.
Bye.
Thank you. Good afternoon. Now we are at the position to start our tutorial session of today's lecture, of today's session. The tutorial session will be taken by myself, Dr. Bhavna Singh. I belongs to Jabalpur Engineering College from Physics Department. I have nearly 18 publications in international level. From the last 16 years, I'm servicing at JEC Jabalpur. Today's my talk is based upon the analysis of XRD, where we will deal with some mathematical and analytical calculations to find out the lattice parameters. Yesterday, we have a talk with Dr. Kodam Yugandhar, where he explained about the GSAS software to find out the values of HKL parameter and the crystal structure. But today, we will go through the basic understanding of the mathematical and the analytical methods by which we can identify the crystal structure as well as HKL parameter of this particular sample. So, here I am going to share the slide for the today's presentation. Just a minute. So before start, so this is my first slide where I'm expressing that the course is based upon the nanomaterials by design for energy applications, and this one is the tutorial number 2. First, we are talking about X-ray. That therefore it is necessary to know what are X-rays. The X-rays are the electromagnetic radiations of exactly same nature of light, but of very much shorter wavelength. The region of X-rays lies between the range of gamma rays and as well as UV rays of the electromagnetic spectrum. How the X-rays are generated? X-rays are generated when there is a deacceleration of the fast-moving electron when they collide and interact with the target anode. In this process of deacceleration, more than 99% of the electron energy is converted into heat, and only 1% of energy is converted into the X-rays radiation. It shows that a high amount of energy is converted into heat, where a significant, that is only 1% of energy is converted for producing the X-rays beam. Now, the question arises why we are using X-rays to identify the crystal structure. The X-rays have the wavelength similar to the interatomic spacing of the atoms. Therefore, it is useful to explore for the crystal structure. As it is a non-destructive analytical method, therefore, by using X-rays for any identification of the crystal structure, the sample will remain same. There is no any distortion will produce because of the X-rays beam. Therefore, we are using X-rays for identification of the crystal structure as well as orientation of the lattice. As we says the term XRD, that is X-rays and diffraction. Now, we should be aware what is diffraction. Diffraction, in simple term, diffraction refers to the apparent bending of waves around small object and the spreading out of the wave past small aperture. But when we talk about the crystalline wave, or for the crystalline sample, in case of crystallography, diffraction is the scattering of coherent waves by the atoms in the crystal. The diffraction pattern results from the interference of the scattered waves. The next slide shows the X-ray diffraction basis. As we know, the X-ray diffraction is one of the best tools to identify the crystal structure. Here, the wavelength of the X-rays which we are using for the diffraction purpose should lies in the range of 0.5 to 2.5 angstrom. When the intense beam of X-rays strikes the crystal of study, it diffracts the X-ray beam depending upon the crystal structure and orientation. It means then what is the structure of the crystal. Therefore, when the X-rays are struck with a particular atom at a particular position, then the reflection will happen and it will create a spot on the detector, and which is measurable, and by measuring the particular intensity of the spot as well as the position of the spot present or shown on the slide, we can identify the nature of the crystal, or we can identify the crystal structure. This is the particular graph what we obtained with the XRD. Here the y-axis shows the intensity of the X-rays, whereas the 2 theta values shows the angle of the reflection. The effect of path difference. Difference in the length of path travel leads to the differences phase. Shows that if there is a difference in phase difference, there is a difference in phase, then the path will be differ. In a similar fashion, the introduction of path phase difference produces a change in amplitude. It means when the two traveling waves having the different phase, then the resultant amplitude will be differ. For example, here we are showing that the two waves which are moving in a particular direction, then the resultant wave will, if both are having the same phase and there is no any path difference, then the resultant wave will be a summation of both the two waves. Therefore, the amplitude gets higher position. And this phenomena is termed as constructive interference. And the condition for the constructive interference is that path difference is equals to n lambda, where lambda is the wavelength and n is the particular order. In a similar fashion, when we talk about the destructive interference, where both the two waves are perfectly out of phase, that means the phase difference is of 180 degree. Therefore, the resultant wave will show the straight line, and it shows that there is no any peak obtained on the XRD structure or XRD spectrum. This is the simple basic understanding of the Bragg's law. Let us consider that these two planes defines the arrangement of a particular atom in a structure, in a lattice plane. Let us suppose that two incident waves that in the terms of X-rays or incident XRD are XRD travels in a particular direction and they strikes over the atom of different planes, where the plane difference is of D. That is the interplanar spacing between the two lines or the two planes is of D. Then after reflection, they will move in some other direction, where the second waves will travel some more distance as compared to the first one. And this is something something about d sine theta angle. When we measure when we calculate the distance, this extra path will equals to d sine theta. Therefore, the total path difference between the two reflected waves is of 2 2d sine theta. We get the X-rays or XRD curve on a particular structure only when there is a constructive interference occurs. And the condition of constructive interference is equals to n lambda equals to 2d sine theta, where n is the diffraction order. What is Brevis lattice or what is lattice? Lattice is a particular position of atoms in a crystal structure. When we talk about the Brevis lattice, it refers to the 14 different three-dimensional configuration into which the atoms can be rearranged in a crystal. These are the 7 types of structures or the 7 type of lattice, where the primitive body centered and the face centered are the different type of arrangement of the atom in a particular structure. ABC is a lattice distance where alpha, beta, gamma is the angles. D spacing or the lattice spacing or interatomic spacing is the distance between the parallel planes of the atom. It is the minimum distance between the two planes. Since in the last slide, we have seen that in the Brevis structures, there are 7 types of crystal structures or crystal may be formed. That it's cubic, tetragonal, hexagonal, rhombohedric, orthorhombic, monoclinic, triclinic. Therefore, we have calculated the various type of D spacing for the crystal structures. And the formulas is given like that. We also know that as the crystal symmetry decreases, the number of XRD peaks observed increases. That is, the number of XRD peaks somehow depends upon the symmetry, that how much symmetry is there in the crystal structure. For cubic crystal, the highest symmetry, fewest number of XRD peak, that is 110 equals to 101 equals to 011, because A, B, C, all three have the same interplanar spacing. When we talk about the orthorhombic crystal, where it has a lower symmetry, therefore we will obtain the higher number of XRD peaks, as A, B, and C are not equal to each other. Therefore, the condition of the HKL parameters will not be same. Indexing diffraction pattern. Now, what is indexing? First, for any type of calculation or any type of determination of the HKL parameter, it is compulsory to index all the peaks. Therefore, what is indexing? Indexing is a nomenclature of the particular phases obtained or particular Miller indices obtained in the crystal. So, indexing is a process of determining the unit cell parameters from the peak position. To index a powder diffraction pattern, it is necessary to assign the Miller indices HKL to each peak. So we have to provide the value of HKL to every peak obtained in the XRD spectra. Only correct when all the peaks are accounted for. That means if we initially take 1 or 2 phases and we said the crystal structure is like this, then it is not correct. We have to take all the peaks and find the HKL parameter completely. So what are the information we get by XRD? So with the help of XRD, we can identify the phase, lattice parameter, crystalline size, degree of crystallinity, lattice strain, and dislocations density. These are the all values or parameters which can be obtained by using XRD calculations. Now, the indexing a different diffraction pattern from cubic material. If we have a particular X-ray diffraction which shows the diffraction of a cubic, then how we can identify that what are the HKL parameters, how we can determine the value of these parameters. Then there is a mathematical and as well as analytical method which are used to calculate these. So as we know that the Bragg's law and the Bragg's condition is defined by D and lambda equals to 2D sine theta. D HKL refers to the value of D spacing for Miller indices HKL. Therefore, just by simplification of this equation number 1, we can write equation as 1 by D square equals to 4 sine square theta by lambda square. The D values is also the D values can also represent it for the cubic material, like 1 by D square equals to H square K square L square by A square. Therefore, by combining the value of D with the Bragg's equation, we will define a new equation like this, where H square K square L square by A square equals to 4 sine square theta by lambda square. Just by rearranging the particular equation, we will obtain the equation like this. Here, the value of lambda square by 4a square is a constant. Suppose it is named as k values, where the values of h square, k square, and l square is proportional to sine square theta. That means the planes with higher Miller indices will diffract at higher values of theta. It means if we have HKL like 3, 2, 1 or 4, 4, 4, then the theta angle will be higher. In cubic system, the first XRD peak in the diffraction pattern will be due to the diffraction from phase with the lowest Miller indices. There are 3 types of cubic structures are available. For example, simple cubic, body centered, and face centered. If we are talking about the simple cubic, then HKL parameters will equals to 100. 110 defines the body centered cubic structure, whereas the 111, that is X, Y, and Z. In 3 directions, there is a present of the particular atom. Therefore, it is termed as face centered. Thus, the face centered HKL will be defined by 111, where the value of H square, K square, and L square is equals to 3. Conditions for allowed reflections for cubic lattice. For simple cubic, all possible HKL values. That means H square plus K square plus L square, which defines the cubic structure, is equals to 1, 2, 3, 4, 5, 6, and so on. Only the 7 number is missing here, because there is no perfect combination available for the H square plus K square and L square, which by which we can obtain the value 7. Now, body-centered cubic structure is those where the reflection is allowed when HK plus L is even. Reflection is not allowed when H plus K plus L is odd. That means only for even condition, the reflection is allowed. That is H square plus K square and L square equals to 2, 4, 6, 8. And this is a condition which we can obtain very easily just by using pen and paper. Face-centered reflection is allowed when H, K, and L are either or even or all odd. That is no reflection when H, K, and L are mixed. That is even or odd. That is even or odd condition mein will not get any type of pattern. Therefore, for face-centered, H square plus K square plus L square is equals to 3, 4, 8, and so on. These are the value which we obtain by simple mathematical calculations. As I said earlier, there are 2 methods by which we can obtain the lattice parameters HKL. Here, I'm showing the first method, mathematical expression, or the mathematical method to obtain the mathematical method for indexing cubic crystal. These are the steps shown here. First, here we are having a particular XRD of the aluminium, where the wavelength of the XRD is 1.54 angstrom. We'll get some intensity and the 2 theta angles represented here. Now, how to find the lattice parameter of this crystal? Therefore, we have to use the following steps. First, we have to identify the peaks, then determining the sine square theta value. Calculate the ratio sine square theta by theta minimum and multiply by the appropriate integers. Now the selection of the integers is based upon the conditions shown earlier. Select the result from the step 3, that is H square plus K square and L square as an integer values. Now compare with the sequence and will identify the Brevis lattice and then calculate the lattice parameters. Suppose these are the peak number, 2 theta values for a particular given XRDs like this, where we first identify here our first step is to identify the number of peaks as well as the peak position. Therefore, the peak position for a particular aluminium is 38.43, 44.67, 65, and so on, which is shown here, 38.43, 44.67. That first we have identified the peak position, and the table is given like this. The second step is to obtain the sine square theta values. Here it is to be noted that sine square theta value should be in radians only. If it is in degree, then we'll not get the correct position or the correct HKL values. Therefore, first it is compulsory to convert it into the radians. Then only we can find the sine square theta values. In the step 3, we have to multiply with a particular integer and divide it by the sine square theta minimum value. For the cubic structure, allowed states are 1, 2, 3, 4, and so on. Therefore, we have multiplied with 1, 2, and 3, and later on, up till we get a constant number. The theta minimum, which we obtain from the sine square theta, is 0.1083. Therefore, we divide each value by 1083 and obtain the value of the first column, next second column, and then third column, and so on. Here we obtain that when we multiplied 3 into sine square theta by sine square theta minimum, the values is like 3, 4, 8, and so on. It shows a complete integer form. Therefore, this one is the best values which we obtained by the multiplication of a particular integer. Now, we'll take this particular value for calculating the values of HKL. So the values of HKL will h square plus k square and L square leads to 3, 4, 8, 11, 12, 15, and so on. When we obtain the value of 3, and if we want to write in the form of h square plus k square L square, then the combination of HKL and L parameters will be 1, 1, 1 for 4, 2, 0, 0 for 8, 2, 2, 0, and so on. By this way, we can obtain the value of various HKL parameter. And if we look over this particular value of h square plus k square L square, it shows that the best criteria for face-centered cubic structure, that is the condition for the face-centered cubic structure, the value of h square, k square, L square must be equal to 3, 4, 8, 11, and so on. So by just observing these, we can conclude that the particular crystal structure is of face-centered cubic. Now, the last step to calculate the lattice parameter is to find out the value of A. Since in the cubic structure A equals to B equals to C, therefore we have the formula to identify the value of A, and by using the formula shown earlier, we can obtain the value of A for different theta values, and then by averaging we will get the perfect value for the crystal structure or the average value. Now, this is the one method or the mathematical method by which we can calculate the HKL parameters. Now, in the next slide, we'll discuss the analytical method. Now, mathematical method is based on the complete mathematics involved, whereas in the analytical method, we'll get some approximation also. We have to consider okay, now we have to select this particular value for our calculation, and this values will give the best result for obtaining the structure. And these are the particular steps by which we can identify or we can index the cubic structure analytically. So the first step again is to find out or to identify the peak, then determining sine square theta values. Here, instead of sine square theta by minimum, we have to divide sine square theta by a particular integer. Identify the lowest common quotient and identify the integer to which it corresponds. And let the common quotient be termed as k, divide the values, and we have to follow the particular steps given here. Now, when we define the peak location of a cubic crystal here, then first we have to again calculate the value of sine square theta, and the sine square theta is in radians, then it will looks like this values. Now again we have to divide by the number of integer values like 2, 3, 4, 5, 6, and 8. Again the 7 is missing. As I said earlier, h square plus k square L square will not leads to the value 7, therefore 7 is missing. These are the values which were obtained, and the values are shown here. Now, as we see, by sine square theta by 2, sine square theta by 3, sine square theta by 4, the common quotient is 0.0361. That means this particular values appears mostly. So this is the common quotient and defines by k. Now, our next step is to divide the sine square theta by k for each peak. Select the approximate pattern of h square plus k square plus L square values and identify the Brevis lattice, and then calculate the lattice parameter. So here we divide the value of sine square theta by the factor of this 0.0361, and will leads to these values. Now again we can see that the values are 3, 4, 8, 11, and so on, which was same as we get in the mathematical calculations. That is the first method for identification of the peaks. So again, h square plus k square and L square leads to the various HKL parameters like this. Again, it shows the FCC structure of the cubic crystal, and the lattice parameter can be calculated by using the formula A equals to lambda upon 2 under root of k. The value which we obtained for A is again equals to 4.0541 angstrom. It shows that whether we are doing the calculation with the mathematical method or with the analytical method, the result are same. That means for a particular cubic structure, we can use both method to identify the value of HKL, where we have to taken into consideration that all peaks should be covered properly. Is there any question between? No? Okay. Now, this is somewhat method which are used to identify the indexing, and to indexing the non-cubic crystal structure of XRD by XRD. Let us consider the structure is hexagonal. Let us assume that. Therefore, for the hexagonal structure, the formula is given like that, where we have rearranging both the formulas by using for the Bragg's law as well as D values, we'll get the equation like this: sin square theta equals to lambda by 4a square, and so on. Here, this particular constant is represented by A, which is equals to lambda square upon 3a square, and the value is represented by C is equals to lambda square by 4c square. Just by observing h square plus hk plus k square, k square, will get the constant value A, and A equals to lambda square by 3a square. H square plus hk plus k square equals to 0, 1, 2, 3, and so on. The L square is calculated only when the values are like 0, 1, 4, and 9. Here is a question by Mr. Yogesh. This is for cubic. What is the procedure for other method? Yogesh, I am explaining the structure for the hexagonal structure now. The cubic is already over. There are already two methods which we talked earlier: analytical as well as mathematical method. And this particular procedure is we used for the non-cubic structure. Here we are taking the example of hexagonal structure. So just by rearranging the equation, we can identify the value of C also. Now, these are the steps which are involved in the calculations of non-cubic material. So non-cubic material may be of hexagonal or orthorhombic or whatever the material. We have to follow these steps, and somewhat basic rule we have to change. Now, the first step, again, if we have the XRD spectra of a non-cubic structure, then first step is to identify the peak position. Then initially we have obtained the peak position by using the XRD spectra, and the peak is given by 35.100, 38.390 up to 119.280, and so on. Here the intensity value is also shown. The intensity ratio is very useful to identify the original crystal structure and the position of an atom in a system. Now again, we have to do the value. We have to obtain the values of sine square theta, and the sine square theta is again in the radian. Then the value so obtained is shown here. Since it is an hexagonal system, therefore the integers like 1, 3, 4, 7 or 10, 11, 20, 21, and so on, by which we have to divide the sine square theta values. So in the first step, that is in the column number 4, we have divided the sine square theta value by 3, next by 4, next by 7, and so on. So here is here we get the complete values just by dividing the integers, just by integers which are shown here. So when we observe it completely, we find that 0.098 or 096 is a particular value which is coming continuously in every rows. Therefore, this value is considered to be a constant value termed as the value of A. Now, in the next step, we have to divide the value of sine square theta by A. So we'll obtain the integers value. Here, it is 1, 1.2, and so on. So 1 sine square theta by A refers 1. It means the value of h square plus hk plus k square is equals to 1. Then we have to find what is the best suitable conditions for HKL. Here, since we are using this particular equation, therefore here is it to be considered that the value of L parameter is 0, because h square plus hk and k square or h square, the L is missing. Therefore, L is always considered to be the 0. Then the best condition or the best suitable values for h and k by which we can obtain the complete integer 1 or 3 or 4 is like this. Therefore, these are the combination which shows the HKL parameters for the particular combination. When we go to the next step, here what we have to do, we again have to find the value of the next parameter C. So what is the method to obtain the C? That means we have to rearrange the equations which is shown earlier like this. Here, to obtain the value of C, L square equals to sine square theta minus A into complete HKL values for first condition. Therefore, by doing this, we can obtain the value of C. So again, we have to do what? So again, sine square theta minus A, sine square theta minus 3A, sine square theta minus 4A, these value is to be identified. Therefore, we have obtained these values like this. Again, we observe that the most or the least common quotient is 0.1083. This is the value which is available in most of the rows. So again, LCQ equals to 0.1083. Now look at the common quotient LCQ. From this, we can identify the value of 00L. As we know that the crystal structure is hexagonal, therefore the first followed or the first allowed peak will be equals to 002. That means H and K is missing. Only we are talking about the value of L. Therefore, L square equals to 4. That is the best or the first allowed peak in the hexagonal system is equals to 002. Therefore, the values of C is to be obtained by following the equations of C equals to LCQ upon L square. So, again, we can obtain just by observing these values, we can calculate the values of L square equals to LCQ by C. And if it is 4, then the parameters will be like that 002. If it is 16, then the parameters or the HKL values will be 004 and so on. Now the question arises how we can obtain the value of 102. Now here we identify the fourth peak as 102 because we observe that LCQ for sine square theta minus 1a, that is 1a. Then recall that from the first or 1 come from the quadratic equation where h square plus hk plus k square equals to 1. Therefore, this value is to be taken account, and here again the L value is 2 where the values of h and k must be 1 and 0, by which we can obtain the values of HKL and so on. This way we can identify the values of rest of the peaks too. Lastly, what we have to do again, we have obtained the values of sine square theta. Now all the HKL parameter is defined and calculated. We again we have the equation sine square theta equals to C into L square plus A into H square plus HK plus K square. Earlier we have calculated the value of C as well as the value of A. The value of C and value of A is value of C and value of A is LCQ equals to 1083 and A equals to 0.098. By this, we can obtain the value of C, and the value of C is 0.271. So we know the value of A and C, and just by putting this value of A and C in the equation and by keeping consideration into the values of H, K, and L, we can calculate the different values for sine square theta. Just by obtaining the values of sine square thetas, we can identify the value of lattice parameters A and C for the hexagonal system by using this formula. A is calculated by lambda upon root of 3a and C is equals to lambda upon 4a. So this is all about the calculation of hexagonal system, and by this we can identify the values of the different lattice parameter, say A and C. This is all about the calculations for calculations by XRD for the cubic as well as for the hexagonal system. I think this is completely a mathematical type of phenomena by which we can identify the values of different peaks. So you must try firstly for a simple cubic structure and for go later on. It is quite difficult to identify the structure of orthorhombic or hexagonal or any type of crystal other than the cubic. So first you try your level best to identify the values of cubic structure. I think it is based upon the total practical or the practice session. So you first take any random or the any XRD pattern and calculate by yourself. If there is any doubt regarding calculation, you may personally mail to me and will definitely do work on that. I think there is no question. So we have to stop the session. The next session will be start tomorrow by 10:30. Okay. Thank you.